Welcome back. This is Dr. Ron Prefer from Western New England University. This is part 3 of a multi-part tutorial on preparing you for any type of testing you may have for medicinal chemistry. So the first two parts we talked about general acids and bases. Now last tutorial was on acids listed above. Now let's focus on bases, what basic functional groups are and how they're different. And I mentioned differences throughout, but this is where students have the greatest difficulty. The difference between an acid and a base. They understand the difference, but how it means, how it correlates to other things. So typically a base is something that accepts a proton. And right off the bat, I'm going to get this into your head. You think of a base, you think of neutral and plus. Acid, neutral, and minus. So constantly pound that into your head. Acids are neutral or minus, bases neutral or plus. So a molecule is a base if it has the ability to gain a proton, and therefore if it gains a proton it will become plus. The key thing is there needs to be a pair of electrons in order to do this. Now we typically draw this as like a B minus, and that's basically the more electron density that's around that B minus, the more able it is to grab a proton because it'll have more negativeness to it. Likewise, if you have electron withdrawing groups, it'll decrease the ability to grab a proton. So if we look at this value here, this next statement is where people have the biggest problem. The pKa can be used to compare relative acidity after it has been protonated. So when someone tells you the pKa of a base, whether it's a professor, a textbook, or even this tutorial, it's a lie. The pK value that they're presenting is after it has accepted a proton. Therefore, by definition, that molecule is now an acid. We have cheated throughout our careers, I do it too, for simplicity, but the truth is it needs to be protonated in order to have a pK value. So therefore, when you're using pK, this expression is actually that expression. And then everything else falls nicely into place. If you can get that in your head, everything should fall nicely into place. So therefore, this equation means a low pK value, the reaction is to the right. A high pK value, the reaction is to the left. So again, this is what I'm stating. And if you listened to earlier presentations, I said this. It's the same thing. Exactly the same thing. I've just now made the base into an acid, and now I have one rule for everything. And the reason we do this is because we want to use pKa, not pKa and pKb. It makes life more difficult. We're making life easier here. So let's actually make up some rules. Not make up some rules. Let's actually develop rules. The lower the pK value, the stronger the conjugate acid. Ability wants to lose a proton. So let's get that in our head. Let's think about this. The lower the pK value, so I'm comparing a 2 to a 10, the stronger the acid. So if I am a molecule that has a pH of a pK of 2, I am a strong acid. If I'm a molecule that has a pK of 4, I'm still an acid, but not as strong. A pK of 10, I'm still an acid because I have a pK value, but I'm not as strong. The higher the pK value, the stronger the base. Okay? So again, if I say it has a pK value, it must be an acid. So now, let's go into specific examples. That's where hopefully everything will fall nicely into place. The most common of all the bases that you'll ever see are amines. They can either be primary, secondary, tertiary, but not quaternary. Quaternary does not have a proton. So therefore, it cannot accept a proton, therefore it's not a base. So if we look here, we have a primary amine. There's a secondary. There's a secondary. This is not an amine. It's an amide or an amide. We don't consider an acid or a base. It's, for all intents and purpose, in your body, it's neutral, and it'll always be neutral. So if you ever have an amide, don't touch it. Ignore it. Don't do like so many other mistakes I've seen before. They'll try deprotonating this or protonating it. Ignore it. And here, this is a tertiary amine. So, what is the pK value for these above molecules? Well, we need to know the range, correct? No. They don't have pK values. The amines are unprotonated. And if you'd said, well, let's figure it out, you'd be wrong. They don't have a pKa value. And that's the whole part I'm trying to pound into your head. We need to first put the proton on, and then we can talk the pK value. So, what are pK values of protonated? There's the key word, the word protonated. Primary, secondary, tertiary amines. The range is typically 9 to 12. If you ignore typically sterics, the tertiary amines are stronger because there's more electron donation going to the carbon. And earlier on I mentioned more electron donating it, more electrons there are to accept a proton. But because of sterics, the trend falls apart a little bit. So if you look at here, the primary amines 10.5, secondary, the more electron donation going, the density going in, it's 11. You'd expect this one to be like 11.5, but sterics plays a role, so it drops it in between. It's just a little cute little thing to understand. But what does it actually mean to have a pK of 11? That's the part. Okay? Who cares what the molecule is? I have a pK of 11. I am a molecule that has an H, and that H has a pK of 11. What does it mean? I did a couple of these in the part 2, but let's do it here again. If I'm a molecule that has a functional group that contains a hydrogen that has a pK of 11, that means at pH 11 I exist at 50-50 as this molecule and this molecule, and these molecules or ions or whatever you want to look at it. So this molecule and this molecule at pH 11, 50-50. At pH, we'll say pH 10, 9, 8, 7, any number lower than 11, there's more H plus floating around. More H plus, it'll be pushing it more and more and more into this direction. What if I have pH 12, a higher pH value? Well, if I'm at pH 12, there's more OH minus floating around, which could react with the H plus forming water, meaning it'll more and more will go in this direction. Okay? And that's the important one. I don't care what the molecule is. Start off as a base or start off as an acid. I don't care. All I need to know is that at pH 11, it's 50-50. At pH 10, 9, 8, any number lower, in this case, there's more H plus this way. At any number higher than the pK value, the equilibrium is to the right. So if you are at pH 7.4, will the amine be protonated or unprotonated? Hopefully you can figure this out. Take a moment, press pause, and figure it out. So again, as I mentioned, if you look at what has to happen if you're going from a pH 11 to 7.4, you're becoming more acidic. Therefore, there's more protons to grab. Now, so because we don't have anywhere in our body pH of 11, in fact, I think the highest in our body is 8 anywhere, we don't worry about this. Amines will always be protonated. They'll always be acidic because they have an acidic proton now on it. The anilines is a subclass of the amines. These are aromatic amines. They're not as strong, hence they have a very low, need to be very low for it to be protonated. They have a very low pK value. For example, aniline here, simplest of them all. This molecule here has a pK value of 2.5. Now, a lot of times you'll write pK underneath here of 2.5, just because, again, we're cheating, but it needs to have the proton on there to have a pK value. So the question is, why does it have a lower pK value? Well, very simply, these electrons need to grab a proton somewhere, and if those electrons are being pulled into the ring resonance, can't do it as easily. That's simple enough. Now, if we look at specific examples, let's just go down here. This one here has actually 2 pK values. So there must be 2 functional groups. One of them is acidic. One of them is basic. So right here, this is, if you remember from part 2, this is a sulfonamide, and this has a pK of roughly 6.5. This has an aniline, has a pK of 2. But again, I'm cheating. It's the protonated aniline that has a pK of 2. There is no proton on here. It would have to be, if it's a base, neutral or plus. So let's put the H on there, and now let's ask the question. At pH 7.4, what will the aniline be and what will the sulfonamide be? Okay, well, let's put the H on. We're at pH 2. We're going from a pH 2 up to pH 7.4. There's more and more and more OH minus around, so therefore that H is going to be pulled off, pulled off, pulled off. So this side will look exactly like this at pH 7.4. Here, the H is on there already. Remember, it's an acid, so therefore neutral or negative. At pH 6.48, it's a 50-50 mixture. At pH 7.4, there's more OH minus around to pull off that H. That H is going to be pulled off, pulled off, pulled off. So at pH 7.4, this is going to be negative. So overall, at pH 7.4, it's neutral here and negative there. Other functional groups we're just going to quickly go over. Amines, also sometimes known as unsaturated amines. There's your amine, there's the imine, so you got a double bond in there. Again, these are less basic, hence we'll have a lower pK value. And here we go. We have one thing to note, primary amines. If you ever see a primary amine, you won't see it in a drug, guaranteed. They fall apart quite easily in water. Actually, during metabolism, you'll sometimes find that primary amines form, and they just quickly react with water, go through hydrolysis to form either aldehyde or ketone. But in the end, here's an example of an imine. There's diazepam. This has a pK of 3.4. And I hope some of you who are listening caught it. I lied again. This molecule does not have a pK of 7.4. This molecule has a pK of 7.4. It needs to have the proton on in order for it to have a pK value. Don't get that mixed up. Other functional groups that are considered bases, the hydrazines. These aren't as commonly found in drug molecules. They typically have a pK range of 8, meaning at in physiological pHs they're predominantly protonated. So here's a hydrazine that you can see here. This half of it has a pK of 8, meaning at pH 7.4, any number less than this, there's more H plus floating around, therefore it's more protonated. Excuse me. So your hydrazine hydrochloride is a real molecule on the market. You'll probably be talk about it in cardiovascular disease. It does have a pK value. Typically, it's this proton on the far, this nitrogen that's protonated. This one has been shown to actually be one of the ring ones. It's a very cool thing, but the key thing to note is it's normally this one here, and it has a pK of 6.4. So relatively, this molecules have pK of 6.4, not this. Other ones, amidines and guanidines, these are very basic. Again, they contain nitrogens, but they're very high, typically in the 10 to 11 or 12 to 13 range. The reason is there's a lot of resonance stability, but if you were to draw this correctly, it's the nitrogen that sort of looks like the imine nitrogen that gets the proton here. So here, these have the pK of 10 to 11. These have pK of 12 to 13. Again, very high. So remember, 50-50. Say this has a pK of 12. At pH 12, it's 50-50. At pH 11, it's going to be a lower pH value, more H plus around, so more and more will exist in this protonated form. So here are two common drugs that contain both. This one here, we got an amidine, and the other one is the guanidine, moiety. Some other nitrogen-containing compounds that are considered bases, the indols, pyrols, quinones, pyridines, thiazoles. These are all aromatic. With the indols, the protein will lose its aromaticity, therefore it's not very favored. So again, notice I put the pK values on the bottom. A lot of times you'll see it incorrectly on the top, but it's actually on the bottom. And again, it's always the nitrogen that's going to be protonated. So this is an overarching understanding of how bases work. Again, hopefully the key component that you're taking away is with bases. The base once it gets a proton, is actually an acid, and then we can have a pKa discussion. Prior to that, it's just a base. So hopefully you'll listen to part 4, and now where I sort of wrap it up, why this whole thing is important, and then we'll be going into more depth about calculations and what percentage at a certain point.